Welcome to Lecture 13. This is Section 7.4, Integration by Partial Fractions. So one of the things that we've noticed as we're trying to solve integrals is that when we have things in the denominator, it makes our integration harder, particularly when there are polynomials in the denominator. So we're going to be working on an idea called integration by partial fractions to help us with those situations. So for a couple of things I want you to recall when you're working with something like this, when you have the integral of a number over a linear factor minus a number over a linear factor. These are technically little u subs, right? So we can make u equal x plus 3 on this one. Then du equals dx. And this is kind of like a baby u sub because it's du equals dx. And so when we would substitute here for this first one, we have the integral of 2 over u du. Minus, over here, we'd make our u our x plus 1. And du, again, is dx, so this is 4. And let's make it a different letter just to be sure we don't mix it up. Instead of du, let's use s. So s and ds dx. So that's 4 over s ds. And so this just becomes the integral of 2, we can integrate right away. The antiderivative here is 2 natural log absolute value of u minus 4 natural log absolute value of s plus a constant. And then we just plug our u and s back in. So 2 natural log of x plus 3 minus 4 natural log of x plus 1 plus a constant. And you can actually put these back together. So any of the coefficients come up here as exponents. So this becomes the natural log of x plus 3 squared minus the natural log of x plus 1 to the 4th plus c. And then subtracting 2 natural logs, you can bring that back together if you want, like this. Using subtraction becomes division. And so you get a nice little solution. Okay, so that's how a lot of these are going to end, okay? And you don't have to use the u substitution there if you're okay with kind of that baby u sub idea, right? The derivative of what's inside is 1, so when you divide by 1, it doesn't change your answer, okay? So that's what we want to make sure we remember how to do. Now, when you get to something like this, what do you do with this, right? So here, what we want to do is we want to think about this. You would try u sub, right? You would try, can I sub for u and make that x squared plus 4x plus 3. And then du would be 2x plus 4. Well, that didn't really work, right? So because what I have is negative 2, if I tried to take out a negative 2 to try to make it x plus 4, let's see, that would be du equals negative 2 times negative x minus 2. And this part does not match this part at all, okay? So therefore, u sub's not going to work. So we've got to have another strategy here. What are we going to do in this situation? Well, here's what we could do. What we can do is we can say, let's see if we can split these fractions up in order to make them look more like number 1. Right? The other option here for this particular one is to do something like this. Okay? And this is kind of a stretch, but we're going to do it anyway. So suppose that you have x squared plus 4x plus 3. And let's make that x squared plus 4x plus, and we're going to leave a little bit of space and move our 3 over here. We know how to make substitutions when things are squared plus a number in the denominator, right? We know how to do that from trig sub. So if I can make this a perfect square and then u sub out, then maybe I can get what I want. So to make this a perfect square, I need x squared plus 4x plus 4 wouldn't allow me to factor that as x squared plus 2 squared. But I can't just add a 4 in there because it changes the function. So if I'm going to add a 4, I have to also subtract a 4. And that's going to give me plus 3 minus 4 is minus 1. So these two are equivalent, right? I completed the square in order to make this something squared. Sorry, and there shouldn't be a square under here. Should just be x plus 2 squared. So now, if I make that u substitution and let u equal x plus 2, then, first of all, this was the integral of negative 2, x plus 5 all over x plus 2 squared minus 1 dx. Okay, and now we're going to make the u substitution. U equals x plus 2, and du is just dx. So this becomes the integral of negative 2 times. Now, we have that u equals x plus 2, but on top I have x plus 5. So if we add 3 to both sides, then u plus 3 is x plus 5. So I can substitute the x plus 5 for u plus 3. Then in the denominator, my x plus 2 becomes my u, and this is u squared minus 1, and this is dx. Okay, now, what I would do here is I'd probably split this and turn this into two integrals, right? This becomes the integral of negative 2u over u squared minus 1 du plus negative 6 over u squared minus 1 du. Whoops, because this should be a du. There we go. Now, this one is another u sub. Okay. And this one over here is a trig sub. Notice how complicated this is getting. Okay. So I'm setting this up for a trig sub, and I'm doing u sub and trig sub and all kinds of crazy things. What if we had a better way to go about this one? I think that we do. Okay. Particularly because this is factorable. Right. And so if we can turn that into factors, and we can split it up, we can make it look like that one up above or something similar, okay? So we can decompose our fractions. So that's what we want to be doing here, okay? We want to start thinking about how can we decompose our fractions. So I'm going to leave this one go at the top, and maybe later I'll finish that to get you a formal answer, but it's a little too complicated. So what we want to do is start thinking about how we can work with fractions and decomposing fractions to make it easier, similar to number 1 above. So the first thing we're going to do is take a look and see, we might have situations where the power in the numerator is higher than the power in the denominator. And what we're going to do here is we're going to divide through using long division. So we'll note here, when degree of the numerator is greater than the degree, or equal to, the degree of the denominator, divide through first. Okay, and the reason for that is if you look up above, both of these, the power in the top is smaller than the power in the denominator. Okay, so first we're going to do that. So we're going to take x cubed plus x and divide it through by x minus 1. And if you don't remember how to do long division or synthetic division, here's your refresher. All right, we say, how many times does this go into this, right? And so what do I multiply x by to get x cubed? I'm going to multiply by x squared. Then we multiply it through. So this gives me x squared, x cubed minus x squared. So exactly how you would do normal division, just with polynomials. Then we subtract. Notice I left the space for the squared term, even though all I had next was the x, right? I didn't want to make that too close to my x cubed because I want to leave space for this. Subtract it, and that gives you x squared plus x. And now you say, okay, what do I multiply x by to get the x squared? And that's a positive x. So when you multiply that through, that becomes x squared minus x. Subtract it, and you end up with 2x. So what do I multiply x by to get 2x? That's plus 2. So 2 times x is 2x minus 2. And when you subtract it, you get 2. So what do I have here? Your answer is always the part that's up top, so this part, so x squared plus x plus 2, and then plus this number over your divisor, right? So 2 over x minus 1. So if I bring that over here, then I can say that this integral is equal to the integral of exactly that, x squared plus x plus 2 plus 2 over x minus 1 dx. And now your first three terms are just regular integrals. And this last one is a baby u sub. You would sub for the x minus 1 on the bottom. And du is dx, so it doesn't change anything. So you just have the integral of x squared plus x plus 2 dx plus the integral of 2 over u du. And that's going to give you 1/3 x cubed plus 1/2 x squared plus 2x plus 2 natural log of u plus a constant. And then you sub back. And again, you don't have to do that little u substitution if you've got it under control. But if you're not getting them right, please make sure you keep doing that. X minus 1 in for C for your u, and you're good to go. Okay, so my first strategy is to divide through, because what happens is dividing through turns it into terms that we can handle, right? Polynomial terms. So that's the first thing we do. Next, what do we do and how do we decompose a fraction where we have the power on the bottom is smaller, but not, or sorry, is larger, but it's not just an x, right? If I try to u sub here, I try to u sub for the bottom. Your du is 6x squared plus 6x minus 2. And that's definitely not what you have in the numerator. So what are we going to do? Okay, so we want to think about how we can go from something that is a large polynomial on the bottom down to something that's decomposed to look like number 1, right? Where I have a fraction of something small with an x plus 3 on the bottom and an x plus 1 on the bottom. So something with linear terms, maybe quadratic terms if I can't get linear, okay? Here's how we do it. So the first thing we're going to do is we're going to factor the denominator. So this becomes x squared plus 2x minus 1 all over. We're going to take out the x. That gives us 2x squared plus 3x minus 2 dx. Now you want to factor that denominator. So I'm going over here. 2x squared negative 2. My magic number is negative 4. It's got to add to positive 3. So positive 4x and negative 1x will do it. Then I factor my box. This has a common x, so this is 2x and minus 1, and this is a 2. So my two factors are, so this is the integral of x squared plus 2x minus 1 all over x times x plus 2, right? That's this term here, and then I get this one, 2x minus 1. This is a box and magic circle. Remember that your first term goes in this upper left box. Your last term goes in the bottom right. To get the number in the circle, you multiply the two of them. Then you use the number in the circle the same way that you would use the end term if you didn't have a number in front of the x squared. So I find factors of negative 4 that add to your middle term of 3. Okay, and that in this case is positive 4 and negative 1. I put them in the two empty spots in my boxes, each with an x, and then you factor the box. Okay, so you take out what's in common, make sure that it kind of works battleship style, right? So 2x times x is 2x squared, 2x times 2 is 4x, negative 1 times x is negative 1x, and negative 1 times 2 is negative 2. Okay, and then your factors are those things that are along the outside. Okay, so that's how I get this. Okay, now, here's the rule of thumb when it comes to partial fractions. You always make the numerator, when you decompose, a generic form of a polynomial 1 degree less. Okay, so that means this is going to be equal to the integral of something over x plus something over x plus 2 plus something over 2x minus 1. Right? because when you would combine the fractions back together, your common denominator would be those three things multiplied together, which is exactly what we have in our original. Okay, the question is, what goes in the numerator? So in order to make these proper fractions, I want what's up top to be 1 degree less. So each of these three terms has an x to the first power. So my numerators are each going to be x to the 0th power, which is just 1, right? So I need constants up there, and I need generic constants so I can figure out what they are. So I'm going to let this one be A, I'm going to let this one be B, and this one be C. Okay, so anytime you have linear terms on the bottom, what goes above them in order to decompose your fractions are constant values. Okay. Now, in order to find capital A, capital B, and capital C, I am going to set these two things equal, right? So I'm going to take, and I'm going to do it over here. I have A over X plus B over X plus 2. And I have C over 2X minus 1. And that has to be equal to what I had originally over here, which is X squared plus 2X minus 1 all over X times X plus 2 times 2X minus 1. Okay. Now, in order to solve for A, B, and C, I'm going to go ahead and multiply and clear my denominator. So I'm going to multiply everything by X, X plus 2, 2X minus 1. What that does is on the right-hand side, it clears all that out. And I just get X squared plus 2X minus 1. Okay. On the right, the A cancels, the A term cancels out the X, and I have A times X plus 2, 2X minus 1. Then with the B term, the X plus 2 cancels, and I get X times 2X minus 1. And with C, the 2X minus 1 cancels, and we get X plus 2 times X. Okay. Now I'm trying to solve for A, B, and C. So let me show you the long way, and then I'll show you a shortcut. Okay, so the long way is we've got to multiply all this out and equate our coefficients. So this becomes, let's see, 2ax squared. I've got a 4x and a minus x, so that's 3x, so plus 3ax minus 2a plus 2bx squared minus bx plus cx squared plus 2cx. And that's got to be equal to x squared plus 2x minus 1. So all I did was multiply everything out. Now I'm going to collect my terms. Okay, so the x squareds on the left have to be equal to the x squared on the right. So here's an x squared, here's an x squared, here's an x squared, here's an x squared. Their coefficients have to match up. So on the left, I have 2a x squared plus 2b x squared plus c x squared has to be equal to x squared. If you divide through by x squared, that tells you that 2a plus 2b plus c has to be equal to 1. Okay, that's my first equation. Next, I've got 3ax, a minus bx, a 2cx, and that's got to be equal to 2. So I'm going to have their coefficients be equal. So this is 3a plus 2, nope, minus b. Sorry about that. I'm looking for the blue ones, not the yellow ones. So this is minus b plus 2c, and that has to be equal to 2. And then lastly, I've got my constant terms, and negative 2a has to be equal to negative 1. So this one will make me easier to solve. So negative 2a has to be equal to negative 1. And if I divide that through by negative 2, that tells me that a is 1/2. So there's my first value. Then I can go back here and work through that. So if I plug that a back into my first two equations here and here, that gives me 1 plus 2b plus c equals 1. And 3/2 minus b plus 2c equals 2. And I'm going to move that to the other side. So if you subtract 1 up top, that gives you 2b plus c equals 0. And on the bottom, I have negative b plus 2c. And 2 minus 3/2 is 1/2. Okay, from here, I'm going to multiply the bottom equation by 2. And that will give me the top equation stays the same, 2b plus c equals 0, and negative 2b plus 4c equals 1. If I add those two up, the b terms cancel, and I get 5c equals 1, or c is 1/5. There's my second value. And if c is 1/5, then I can plug that into the 2b plus c, so 2b plus 1/5, and solve for b. So b is going to be negative 1/10. If you subtract the 1/5 over, divide by 2, you get negative 1/10. Okay, all that work just to find that a is 1/2, b is negative 1/10, and c is 1/5. Okay, now shortcut time. Let's go back to what we had up here. So this first statement where we multiplied everything through, but before I multiplied things out, I'm going to start there and show you a shortcut. Okay. So you did all of this, right? You multiply all this out. You multiply both sides by the 3 terms, and you get this nice function here. Okay. Now, the thing is that this has to be true for any value of x, right? So if I plug in a value of x, this has to hold true. So I can make some smart choices for x, and then we'll see if I can get answers, right? Quicker answers. So I'm going to choose x equals 0, and I'll let you think about that for a second, why I chose that. If you plug that in on the left, you get a times 2 times negative 1. The b term and the c term both have an x in there, and that's going to go to 0. So those two terms both go away. And on the right, I get negative 1. So this is negative 2a is negative 1/2, or a equals 1/2, right? So quick and easy, I got to that one. Next, I'm going to choose negative 2. When you choose x equals negative 2, the a term and the c term drop out, and I just get b times negative 2 times, I believe that's negative 5. When you plug it in on the right, that's 4 minus 1. So I get negative 10b is equal to negative 1. And when you divide by negative 10, that gives you b equals 1/10. Hey, that's one we had before, right? And then lastly, I'm going to plug in x equals 1/2. And this one may be a little bit tricky, but we'll go with it. If I plug in 1/2, what happens is the a term and the b term drop out, and we get c times 1/2 times, let's see, 1/2 plus 4/2 is 5/2. And on the right, when you square it, it's 1/4 plus 1 minus 1. Okay, so not too bad. So this becomes 5/4 times c, and 1/4 over here. So if you multiply both sides by 4/5, you get c equals 1/5, which is exactly what I got before. But notice, I did a whole lot less work. Okay, so if you compare the two, right, I did a lot less work. Okay, just by making smart choices of x's. Right, and typically what I'm doing is I'm setting each of those quantities, each of my factors, equal to 0, and plugging in the corresponding x value. Right, that's going to cancel out things for each piece. Whichever way you go about it, we've got our values, right? Oh, wait, hold on. Discrepancy here. I've got negative 1/10 and positive 1/10. So let's go back and check to see which one is right. So up here, we had 2b plus c. And that came from this first equation. Okay, let me make sure that I'm not negative down here. So when you plug in -2, you get b times -2. And when you plug in 2, and 2 times -2 is -4, minus 1 is -5. And then on the right, I definitely get -1. Oh, wait, sorry. This was a silly mistake. When you multiply a positive and a negative, that becomes positive, which means I get a negative in my answer. Whew, so it's -1/10. Sorry about that. All right. Now we've got our values. How does that help us with the integral? We're going to go back and plug in those values. So that means I'm going to have the integral of 1/2 over x minus 1/10 over x plus 2. Notice that I put the negative as a minus sign as opposed to with the value. Plus 1/5 over 2x minus 1 dx. Okay, now I'm going to pull out the number and integrate each term. So that's 1/2 integral of 1 over x dx minus 1/10 integral of 1 over x plus 2 dx plus 1/5 integral of 1 over 2x minus 1 dx. Okay. Now, each of these is technically a u sub, okay, or at least the second two are. But if you're going to use a baby u sub here, that's totally fine. So this is 1/2 ln of x, absolute values, minus 1/10, the natural log of x plus 2. Derivative of x plus 2 is just 1, so that doesn't change anything. Plus 1/5, natural log 2x minus 1, but I've got to divide by the derivative of what's inside. So what's inside is the 2x minus 1, so I've got to divide by a 2. So I'm going to multiply everything by 1/2. And that gives me a final answer of 1/2 ln x minus 1/10 ln of x plus 2 plus 1/10 the natural log of 2x minus 1 plus a constant. Okay, so the actual integration part is usually relatively quick and easy, especially if they're linear terms, but finding the values can be quite tricky. Okay, and if you want to put this all back together, you can as a single natural log, but you don't have to. Okay, but quite a bit going on in order to find our integration by partial fractions. Okay, that was example 2. All right, and we've got one more here. And that is example 3. And this one, again, can factor. So let's factor this one. So this is 1 over x plus 3 and x minus 3 dx. And so this is going to be the integral. These are both linear terms. So x plus 3 and x minus 3. And what do I plug above them? So these are linear factors. So a 1 degree less would be a random constant, would be a and b. Okay. So I need to go and find them. I've got a over x plus 3 and b over x minus 3 has to be 1 over those two multiplied together. Multiply both sides by x plus 3, x minus 3. That's going to give you a times x minus 3 plus b times x plus 3 is equal to 1. Okay, here's where I'm going to use my shortcuts. If you want to multiply it out and equate coefficients, go for it. Notice that there are no x's on the right, so your ax plus bx is going to be equal to 0. But I'm going to use choices of values. So if I let x equals 3, that means the a terms goes away and I get 6b equals 1, or b is 1/6. If I use x equals -3, that's going to give me -6a. The b term goes away and that's equal to 1, so a is -1/6. Okay, and I'm going to go plug those back in. So that's going to give me the integral of -1/6 over x plus 3 plus positive 1/6 over x minus 3. And I'm just going to pull that 1/6 all the way out front. From here, we're going to go ahead and take our integral. So this is 1/6 times negative natural log x plus 3. The derivative of the x plus 3 is just 1, so we don't have to compensate for anything there. And this is the natural log of x minus 3. Again, derivative is 1, so we don't worry about it. So you get -1/6 natural log x plus 3 plus 1/6 natural log x minus 3 plus a constant. And again, if you want to put those back together in a single trig function, you can. But this answer is completely fine. Okay. Now notice that each of the examples here that we did were linear factors, right? Underneath the fractions, I had linear terms, ax plus b's, which means above them we put a constant, okay? But here's your little cheat sheet, so what happens if we don't? So when you have your factor is x minus a, x minus a number, right? You put an a above that, right? A linear term. So even if you had ax plus b on the bottom, you're going to put a random a or b on top, okay? What happens if you have something squared? And this is a little bit tricky, but you repeat it twice. So I get a over one of them and b over that thing squared. Okay. And then for anything that's a higher power, you want a generic thing above it that's 1 degree less. So if I have a quadratic on the bottom, then I want a generic linear term up top. So an ax plus a b on the top. Okay. If I had something that was cubed, I want an ax squared plus bx squared plus c, right? A generic polynomial that is 1 degree less. Okay. And that's what we do. And we'll see some of those, I think, in the guided practice problems.